Hello everybody, my name is Mohammad Noor
And I am Arnav Nagaria.
and today we're going to be presenting our second project for our course EW2 titled Sun Tracker for Portable Solar Concentrator. The motivation for our project is solar power effectiveness. Although solar power is becoming increasingly popular due to its environmental friendliness and cost effectiveness, questions are being raised on the efficiency of solar panels. This efficiency is often limited by the stationary positions and configurations that solar panels are put into, and they are not able to track the sun's movement throughout the day. Studies have shown, as we have quoted within our presentation, that stationary solar panels produce up to 25% less power as compared to ones that track the sun's movement. This stationary configuration results in a significant reduction in the amount of solar energy that can be harvested. In this project, we aim to maximize the output of a solar panel by constructing an automatic sun tracking device. We employ the usage of LDRs and a simple comparator that we have built using electronic components in our lab to do so. And by doing this, we expect to significantly increase the amount of solar energy that we can harvest from a basic, simple solar panel. These are the papers that we have used in order for us to be able to derive a motivation for our device. The three papers were extremely helpful in providing us with an insight as to previously conducted studies, both comparative and analytical, in order for us to be able to have a basis point to begin building our device. Here, we have provided a summary of the three papers that we have used in order for us to derive a basis point and an insight into our device. The first paper, titled Comparison of Static and Single Axis Solar Tracker, compares the power performance of static and single axis solar tracking systems. It employs the usage of a Berger-Duffy model to track the sun and uses an MPPT, or a maximum power point tracking method, to estimate the power. The second paper, titled Design and Implementation of an Automated Dual-Axis Solar Tracker with Data Logging, is a preliminary data analysis paper that shows how a fixed solar panel orientation is less power efficient as compared to a dual-axis system. It employs the usage of an Atmega 328 based microcontroller and two servo motors for dual-axis control. The third paper, titled Design and Analysis of Automated Dual-Axis Solar Tracker Based on Light Sensors, demonstrates the efficiency of a simple dual and single-axis tracker and how they are up to 25% more efficient than conventional stationary models.
Here I want to talk about the preliminary design and initial thought process. Our initial design employed the use of two separate op-amps to compare the voltage difference between the two LDRs and use this to drive a DC motor using a stepper motor IC. Two MOSFETs were included to amplify this voltage. The unavailability of components such as stepper motor driver and the stepper motor itself forced us to employ a different design strategy after consultation with our project mentors. The image shows us the simulation image and our circuit design for our initial thought process. Preliminary design, finalized thought process. Our new and improved design ideology seeks to optimize single-axis solar panel usage by minimizing power usage. This new design uses a servo motor, a more commonly available one, instead of stepper motor. The way we approached this optimization was to use plotting methods to analyze the intensity of solar energy and use the data collection to find optimal solar angle. We went ahead with the construction of a device that not only tracks solar intensity but also optimizes it with the aid of simple RTC module to ensure optimal times for all these solar angles. As can be seen in the figure, our block diagram includes a solar panel with two fixed LDRs on opposite sides. This is used to compare light intensity on both ends. A simple use example is, if the light intensity at the left LDR is higher, the voltage is higher, and this will result in rotation of the solar panel to the left. Similarly, this is done if light intensity is higher at the light LDR. This is done over about 120 degrees, and this results in the solar panel directly facing the point of highest light intensity.
As can be seen in the figure right now, the circuit diagram involves the usage of a simple microcontroller. The choice of microcontroller is the Arduino Uno. We have also employed the usage of an RTC module. that has been included in the circuit diagram.
In our simulation and verification stage, we used Tinkercad and Multisim, the two very powerful and efficient software tools to graph our designs on a software level.
As can be inferred from figure 4, which represents the Multisim simulation graph, the two blue lines, the dark blue and light blue, represent the input signal to the op-amp from the output voltages of the LDR. The underlying grey graph represents the overall output of our device. When the two signals, the light blue and dark blue signals, are equal in magnitude, this results in the LDR stopping at a constant value. However, when one of the signals increases in magnitude in comparison to the other, the solar panel rotates in the direction of that LDR, resulting in a constant value at that particular instant. After the completion of our ideation and design procedure, we have now come to the building of the final board circuit. The final board circuit was built on a PCB with the employment of jumper and connecting wires in order for the circuit to be clearly understandable. The realization of our final board circuit was included with a simple verification check, which, to confirm our voltage values and the functioning of our circuit, prints onto the Arduino serial monitor the value of the voltage difference between the two LTRs. This voltage is read using the analog pins on the Arduino using the analog read function of the Arduino IDE. The working of the circuit is demonstrated in the embedded video in the next slide. We have also included the RTC module in our final board circuit so as to be able to measure these values of the voltage difference at different intervals of fixed time. As can be seen from the video, our device is successfully performing the required function. The light source used to replicate the sun is a smartphone light.
Test summary, voltage analysis. The graph in the figure shows us the variation of voltage with the angle of the solar axis without tracking. We can see from the graph that our voltage varies from 125 to 160, which are values given by Arduino IDE's analog read function. We use a constant sweep to find the maxima. We have restricted our observations only to the upper half of angles as the region under the plane of the solar panel is of no interest to us. However, when we track a particular light source, the rotation of our device was very limited before it reached its maxima, as shown in the figure 9. Therefore, consuming less power and more importantly, verifying our device capability to accurately track the maxima. And we can also verify it using our serial monitor print.
We would now like to test our device for its power efficiency, as this was our main goal. Our approach to calculate the power of the solar panel was to use the simple power formula as shown by the figure, using the voltage across it. We have also taken into account the internal resistance of the solar panel, as we needed our power to be accurate. Therefore, we first calculated the internal resistance values using the formula as shown in figure 13. Table 1 shows the different values of calculated internal resistance for different values of the load resistance. The average value that we reached at was 21.87 ohms for our solar panel. Table 2, on the other hand, is a comparison between different models. Number 1, the tracking model, and number 2, the static model at different times of the day, and the power the solar panel is able to produce at these different times in different configurations. As can be inferred from Table 2, at different times, different approaches perform better. With the aid of the RTC module, our device successfully hybridizes both approaches, hence being both power efficient as well as energy efficient. At last, we arrive at a graphical representation of these two models besides each other, as can be seen in figure 14, which shows the different approaches or different configurations for the solar panel. This graph shows the produced power for three models: our model, the static model, and the tracking model. As can be inferred from the graph, our model performs better than both these models. However, it is more power efficient than the tracking model, since we are only tracking at specified points.
Having completed our design and building of our device, Here are some proposed improvements. Hardware design. While the circuit is soldered and constructed properly, the overall physical durability can be improved upon. Further improvements on the project could be to employ the usage of ESP32 and related device to push real-time data onto cloud, from where dashboard implementations and remote access can be added.
Our device is extremely power efficient. This, however, can be improved upon by using the angle values of the zenith and azimuthal angles that can be obtained using a GPS sensor. The angle of the solar panel is the cosine inverse of the products of the cosines of the zenith and azimuthal angles. We would like to now demonstrate the few challenges that we faced. Number 1, flimsiness of the circuit as a result of structurally weak components resulting in restricted mobility. This was overcome by the efficient usage of appropriate structural components, including tape and glue guns. Number 2, unreliability of components such as LDRs and op-amps. This was overcome by pre-testing the components in a separate testing circuit before integrating this with our device. Number 3, power restriction. As we did not want to take up more power than a conventional circuit for a low power application, we overcame this by cutting down wherever we could. Example, using an RTC module.
In conclusion, we were successfully able to implement the device and make it power efficient, as seen by the test summary. We were also able to optimize the circuit by integrating the RTC module that aids in optimal deployment over optimal times.
Overall, we feel that we have not only fulfilled the project requirements posed by the problem statement, but have also gone the extra mile by optimizing the device. Thank you.